The study of what's known as machine learning started to bloom. And machine learning is the study of algorithms and mathematical models that computer systems use to progressively improve their performance on specific tasks. So those algorithms build mathematical models of sample data, known as training data, in order to make prediction of decisions without being explicitly programmed to perform the task. So, for example, in this case of what we all have in our mailbox, a spam filter, the more emails you throw at the algorithm, and the more information you provide it with, like this email is a spam versus this email which is not a spam, it knows better to classify future emails. And that's a good example of machine learning. And there is nobody who's reading all those emails and trying to write code saying like, if the sender is X, then this is likely to be a spam. No. What they do is just using a neural network with things which are very similar to those perceptrons, and change the weights of those and extract the parameters from the emails, and the network teaches itself over time to be better and better. One major breakthrough was the invention, if you will. I like to think about great inventions in math as in fact discoveries, because the math was there all the time. We just didn't know it. But a couple of guys came pretty much at the same time to research and discover the what's known as backpropagation using gradient descent. And those guys, Jeffrey Hinton, who's the godfather of deep learning, and Jan LeCun, who today serves as the director of artificial intelligence research in Facebook, but back then was a young French PhD. I don't know if he was still a PhD student or postdoc student. Anyway, they were working on those neural networks, and one of the hardest problems of teaching or training those networks was, how do you update the weights? How do you figure out what numbers you need to put there on the perceptron dendrites, if you will, to teach it properly? And what they figured out was that it's a problem of optimization. You're trying to minimize the error probability on predicting a certain outcome on a training set. And to minimize that, they figured a way which I can only describe as follows. Imagine you're dropped somewhere on Earth. Think about this topographic map I show on the right. You're dropped somewhere on that map, and you need to find the lowest point. So what the backpropagation, what the gradient descent does, is as follows. I'm standing on a point, I'm looking all around me to find the place with the strongest downslope. I pick that direction, I make a step, and then I repeat. I look again around me and find the place with the greatest descent, make a step in that direction, and so forth. And eventually, I hope to get to the lowest point in the map. Now, will that always work? The answer is no, because if I'm dropped in the middle of a volcano crater, I will pretty much be limited to walking inside. I will think I reached the very bottom, right? I'll be locked in what's known as a local minimum. But for certain types of maps or certain types of problems, which are known as convex problems, the global minima is the only minima, and you're pretty much guaranteed, if you follow that process, to end up at the lowest point. So it's pretty hard to show that those networks are really convex problems and so forth, and that you can use this algorithm to find the best predictors, But those guys managed to do that and lay the foundation for the training of most modern networks. And if you remember, I said that the math could be multidimensional. Jeff Hinton, one of, again, the greatest minds in this field, also had the same concern. Give me a second. To deal with a 14-dimensional space, just visualize a 3D space and say 14 to yourself very loudly. Everybody does it. We cannot really imagine a 14-dimensional space, but the math is just the same as 3 dimensions. So it works. One of the famous outcomes of their work, and that was published in 1998, is known as LeNet convolutional network, LeNet for Jan LeCun. This is a multi-layered neural network which takes in scanned digits, like the number 3 you see here, run it through multiple layers of neurons. Every layer contains multiple neurons, and after it's trained, on the right-hand side, you will see the outputs numbered 0 to 9. So those neurons flare up with an intensity which is supposed to be eventually related to the image that is presented. So for example, when the number 3 is presented, the output neuron number 3 would show a probability of 1 or nearly 1, while all of the other neurons are expected to show a probability of 0. And by looking at those outputs, we figure out that it is most likely that the image presented was the number 3. And this animation shows how that works. And you can imagine that this could be useful, for example, for reading zip codes to automatically sort email, not email, snail mail, post office mail. So yeah, and it does quite an amazing work. You can see the numbers running, scan numbers running at the bottom, and the answer showing up at the top. And what you see on the animation on the left-hand side is the activations, all the values of those neurons inside the network during that run. So it's interesting to see. And it actually had some real-life problem which they showed that there are some real-life problems that can be solved with machine learning, even though that those limitations of perceptrons that were discovered in the 60s are valid, but still there are many interesting things we can do. The next development happened in 2012, and that is when we entered the era of deep learning. Deep learning, in essence, is very similar to what we did in the machine learning era, the same the same neural nets, only with more layers, with more data, huge amounts of data, and it can be trained in a supervised manner, in unsupervised manner, and learn multiple levels of representation that correspond to different levels of abstraction. For example, when we see that picture, we immediately would say what? What do you see here? Cat, right. There are plenty of other things in this image, right? There's grass, there's a shadow, there's something red in the background, but we expect every human being to look at that and say this is a cat. And we would like to be able to have a machine or a program that looks at that image and says this is maybe a red-haired cat. So for several years, there was this competition called ImageNet, which was a large-scale visual recognition challenge. And this competition was open to anyone in the world. And people would submit algorithms for image recognition. In that competition, the algorithms were evaluated and tested. And as the organizers put it, the point wasn't just to crown a winner, but to test a hypothesis that with the right algorithms, massive amounts of data in the database could be the key to unlocking AI's potential. And as we will see, that actually happened. That was the driver for the new AI era. One last point to mention is that when algorithms are evaluated, the competition rules were that you're not only looking at the top decision or top classification, but on the top 5 classification. So there were over 1 million images with exactly 1,000 image categories, and if the algorithm would say, like, this is a red-haired cat in one of the top 5 most likely decisions, it would have been considered a success. So that's how it worked. So this competition ran for several years, and in 2012, a guy called Alex Kruszewski presented something new. So this guy was born in Ukraine and was raised in Canada, and he approached Jeff Hinton, the guy we mentioned before, about doing a computer science PhD program in AI at the University of Toronto. And really the fateful moment was when he and his partner decided to make a submission to the ImageNet competition. And their innovation wasn't just what they did, but also how they did it. So what they did is to create a neural network that identifies pictures, identifies images. All algorithms before that were trying to do handcrafted feature detection, like trying to identify eyes or tails or heads in the pictures, and based on that, trying to figure out whether it's a cat, it's a horse, it's a ship, or a flower. What he did, he didn't do any of that. He just created a neural net which was complex enough. So after it was trained with all this database of 1 million images, it would just output a result, like we had with those 10 digits. It would output a 1,000 output lines result. What is the most likely that this image is? So this is the what they did. But the how they did it was also very interesting, because training those networks would take huge amount of time, monthly. Okay, so we're talking about networks with millions and millions of parameters, and the math is very demanding. And what this guy figured out is that he can take graphic cards, which is what NVIDIA does in that case, or AMD, which is the other company that also does graphic cards. He figured out that he can use the same math construct which are used for graphics, which is basically matrix multiplication, and perform the math needed for this neural network on those cards in a parallel manner, much, much faster. And this way he doesn't have to wait 3 or 5 months to get a single result, but he can reiterate his experiments every 2 or 3 weeks. And waiting 5 months is not really an option when you need to get graded this semester. So he managed to pack all that into actually a pair of GPUs, and he crushed the competition. Because in the previous years, you see all those submissions in blue, they reached an accuracy level of about 75%. His submission on 2012, that's the green dot at the top, and this submission got to like 85, I think, % accuracy, which was way, way better than anyone has done before. And the industry was stuck at that level for a long time. And you can see that in the following years, very quickly, all the submissions moved over to GPU-based, AI-based image classification. People just dumped all those handcrafted feature detection algorithms. We figured that's the way forward. So when we talk about modern machine learning, there are three main classes of research and applications. They are called supervised learning, unsupervised learning, and reinforcement learning. I'm not going to go into the deeper level details of what each one means, but generally speaking, supervised learning means I get a lot of labeled data, like images and the label saying this is a cat, this is a sheep, this is a dog, this is a horse, and I use that information to learn. Unsupervised learning does things like clustering. For example, if we have a huge database of consumers and things they are interested in, there exist unsupervised learning algorithms that can cluster them into groups with certain characteristics. And when we, for example, want to market a new product, we can use those classifications to target audiences with those similar characteristics. And there are companies in the US that make their living just out of that, by classifying all US consumers to, I think, like 72 different clusters with very specific characteristics. So they help companies figure out how to best market their product. And I'll talk about reinforcement learning in a couple of slides. Another way to look at progress in different fields in which AI affects our life is that this is broken down into, today, mostly into work on images, which began in 2012 with classification, and then continued to detection, being able to put a box around a car or a pedestrian, autonomous driving, for example, that's detection. And later on, segmentation, the ability to indicate for each pixel in an image, does it belong to a person, does it belong to a car, does it belong to the road? And this is very important for path planning and again, autonomous driving applications. A second class of applications is around language, and that began with sentiment analysis, which is what, say, Amazon does in order to figure out if we like a product or we do not like a product. It actually goes into machine reading human responses. Like if you write feedback on a product, not just give it 5 stars or 3 stars or 1 star, but actually write something. Machines today can read that and typically figure out whether this was a positive feedback, in which case they would like to maybe share that on Twitter or somewhere, or whether it was a negative feedback, in which case they would like to flag the support teams to provide a response. Okay? So this helps companies sift through a sea of data without having a human going through all those responses. And another application is translation. You all know Google Translate, for example. Google Translate went through a similar transition as those image classification competition. Initially, it was handcrafted bunch of algorithms to translate from one language to another. At some point in time, they switched over to using neural networks and artificial intelligence, and there was an overnight, literally overnight, jump in capabilities. Improved substantially. People noticed. The latest on the language front is the auto-answer feature, which many of you might have noticed just this year, or actually last year, on Gmail, for example, on your phone or on your computer. Gmail, when you get an email, now present you with some options of responses. You can choose one of several responses, and in I'd say like 50% of the time, those are meaningful and useful responses that you can actually use. It also does auto-completion today. start typing a sentence, and it gives you like what it thinks you should be writing next, and you can just click tab and get this auto-completion of your sentence. So those are advances in the language field. And then there's the decision-making field, which started with recommendation systems. Again, figuring out what people are buying in order to recommend products, movies, songs, etc., and continued to the field of anomaly detection, which is used mostly today for computer security and network security. So I want to jump into an example of reinforced learning, and that's Google DeepMind. DeepMind is a UK company bought by Google, which developed an AI that plays Atari games. So I'm not sure if you can read the text, but I'll try to explain as it goes. So we started with 10 minutes of training, and this is how it plays. Not very well. Kind of figured out that in some cases it's good to be in the corner because you have a higher probability of catching some of the balls, but not very impressive, right? Yeah, so that's 10 minutes of training. Okay, after 120 minutes of training, it plays like an expert. And the only thing that they fed this network with, the network gets an image of the screen, it controls the joystick that moves the bar, and it gets a reward, which is a score. And after 240 minutes of training, magic happens. It realizes the tricks of the game and how to beat it. So it creates a hole on the side, and we'll see that in a second. Targets. Okay? So it figured all that by itself. Nobody actually taught it to do it. In March 2016, the Google DeepMind AlphaGo system beats world champion Lee Sedol 4-1 in a week-long challenge match of the game Go. The Chinese game of Go. And that is a really impressive result. And they used something called, well, AlphaGo was a software that beats the world champion, human world champion. But later on, they continued and developed another system. So AlphaGo was trained using recorded games of human players. They basically got a lot of games that experts played and used that to train their network. They later developed another system called AlphaGo Zero. AlphaGo Zero didn't get any human knowledge. What AlphaGo Zero did was playing against, well, multiple instances of itself which were playing against each other. And the only reward it would get was when it wins a game. So every time it wins a game, it knows it did something good. It only knew the rules of the game, the core basic rules of the game, and whether it won or not. And after 40 days, it became the best player. It beat the original AlphaGo systems, and expert human players who played against the AlphaGo Zero lost 200 to 0. Okay, it was pretty decisive. Some of them even said that some moves were so unusual that they felt like they were playing against an alien intelligence. This was not trained with any human information. Another interesting development in the field was what's known as generative adversarial networks, GANs, which Jan LeCun is the most interesting idea in the last 10 years in machine learning. And this is a derivative of reinforcement learning, and because what we're doing here is basically trying to forge stuff. And how do we do that? We deploy two networks. One of them is a generator network, which is the forger, and the other one is the discriminator network, the one that tries to figure out whether it is presented with a true thing or a fake thing. For example, in this drawing, we're trying to fake pictures of wine glasses. So when we present an image of a wine glass to the discriminator network, we know whether it's a real picture or a picture that we took from the generator network. So we can reward the discriminator network every time it figures out if that's the real thing or the fake thing. And every time it fails to determine that, we give a positive reward to the generator network that it was able to fake something that looks like. So basically what we can do with a small database of real wine glasses, we can teach those networks to generate fake pictures of wine glasses and to determine, and those two networks just get better and better over time with every iteration of training. Okay, we can just run them against themselves for enough time until they become really good at what they're doing. So some interesting applications of that, those are some like harmless examples. Creating anime characters. And my daughter does anime. She looked at those images and she said, oh wow, it's really good. It looks like human-grown anime characters, but those were made by an artificial intelligence that was trying to fake anime characters. It can do what's known as image inpainting. Basically, after enough training on a large data set of photos, you can present it with a photo that is missing a part, and it will complete that part. You see pairs of photos here, like a photo with, I think, a bird, and the bird is missing, but the AI was able to reconstruct the bird, okay? Or trees, or other stuff, which is cool. It is able to generate fake music which sounds plausible to the human ear. Okay, sounds good, like the music we were listening to at the beginning. Because it was given a database of music which people consider to be good music, and over time the generator network was trained to generate good enough music pieces that the discriminator network was having a hard time to discern between them and what we humans think is good music. So those are relatively harmless examples. There are some very useful examples, like the ability to do image-to-image translation. For example, at the bottom right-hand side, you see a sketch of a bag being translated into a photo of something that looks like a real bag. And you can imagine how useful that could be for designers, for example. They just draw a sketch, run it through the AI, and they get something that looks like what they wanted. That's real. That's things that AI do. Okay, you can take a satellite image and have the AI generate a map, like roads, after enough training. Another interesting thing is what's known, there's a paper called CycleGAN, which is known as, it's a cross-domain transfer. Basically, the network was taught to fake images which look like famous artist drawings. So you can take a picture, feed that into the generator network. I don't know if you recall, but that in the previous slide we showed that the generator network has something known as an inspiration, a noise that is fed into it. So if we take a photograph and we feed it into that network as the inspiration, it can translate that or do a domain transfer to make our photograph look like a drawing made by Monet or Van Gogh or Cézanne or whoever. So That's a published paper. You can download that today. There are some creepy examples. Okay, those human faces are not real. Those are fake faces created by an AI, and they look very familiar. They look like celebrity images, but they're not. It's a network that was trained to generate faces that look very much like known celebrities. Okay, so that's a little creepy. There's also this cross-domain transfer here, which goes between zebras and horses, and basically takes a horse photo, converts it into a zebra. That looks a little funky. Basically, what it means is that we're getting to an era where you cannot believe photos you see. I mean, it's not just photos; it's videos too. I've seen works creating a video of President Obama saying things he never said. Okay, you can fake that video using again. So it's a little bit of a scary era we're getting into. You cannot believe things you see. It could be generated like that. So the future of AI applications is currently led in the US by the technology giants known as Find Man. It's Facebook, Amazon, Netflix. It's short for Facebook, Amazon, Netflix, Google, Microsoft, and Apple. And the reason for that is the demand for data scientists with AI experience is so high that they are offered just ridiculous salaries, hundreds of thousands, salaries of 500K and not unheard of. So those are salaries that typically only the giants can pay. This guy, Jeff Dean, is leading the Google Brain project, which is one of the major AI superhouses. He's the guy who led the transition of Google Translate, for example. He's like the Chuck Norris of nerds. There are many jokes about this guy, like his ATM PIN code is the last 4 digits of pi, stuff like that. So if you look up Jeff Dean jokes, you find plenty. And one of the things they're doing today is large-scale data collection with an array of robots at the Google Brain Labs. Short video. So basically what they're doing is trying to train robots to perform missions without the manual programming of, move to the left 5 millimeters, go down. Instead, they're trying to get to the point they can tell the robot, take the green box, find the green box, pick it up, and put it on the red box, okay, for example. So that's, and the way to train the robots, to find the right path, do path planning, to do the pickup, there's a lot of challenges here, which they do by using a large array of robots, which are training and getting better and better over time. Another company, NVIDIA, is training robots in simulated environments. This way we can save the cost of the actual robot and basically instantiate as many robots as we want. And I'll let NVIDIA CEO take the stage for a couple of minutes.
Environment. And what we've done here is we imported a little tiny hockey rink. Something simple. The puck is simulated. The ice is simulated. The net is simulated. So this is Isaac learning. And notice in this virtual world, Isaac doesn't have to be just one robot. The way we do it is this. We replicate Isaac a whole bunch of times. And we let them all learn randomly. It's literally learning randomly. And once it starts randomly learning, it gets positive feedback every time it does something good. It gets negative feedback when it does something not as good. Okay? And so all of these robots are learning at the same time. We stop after a while. We take the smartest robot's brain and we replicate it everywhere. And then we can continue. Of course, just hockey. We could let Isaac learn almost anything. We also let Isaac learn how to golf.
That's what the golf
In this particular environment, of course, the grass has to be simulated. the physics of the ball. Now, remember, we didn't show you the beginning of the simulation, but in the beginning, Isaac doesn't even know how to pick up the golf club. It doesn't even know which side of the golf club to use. But because it repeated it so many times, it eventually figured out that the best way to hold a golf club is with the putter on the bottom. Okay?
Hey, Nir,
Yep.
as much as we want to hear all of this, I just need to be respectful of people's time. It's quite after. I know we have a golf meeting that we need to have right now.
So I'll just put on, that's my last slide.
Okay, all right.
And if there are any questions, I'll be here for a few more minutes to wrap up everything. You're welcome to come and ask.
It's making all of us, I think, feel pretty damn insignificant and useless. Yeah, and Skynet's on its way.
Can I make just one comment?
Sure.
First of all, I thought that was great.
Yes.
I mean, it's really fascinating. I subscribe to some science publications, and Big Science is working on a couple of goals for 2025. One of the goals is instead of doing billions of calculations simultaneously, by 2025 they're going to be doing trillions. That's going to have huge impact everywhere, including artificial intelligence. Everything's a double-edged sword. It'll certainly speed up the learning, but also at that point, the encryption we now use, useless. The protection we have, getting retinal ID and thumbprints, all that. So we're going to have to develop workarounds, but what's coming, there are machines that already make better decisions than we do. Chess. Well, Steve's Tesla can change lanes better than a human can. So pretty fascinating stuff.
Although, did you see the video from the Consumer Electronics Show this week that showed a self-driving car taking out a robot that was walking down the street? So now they're actually smart enough to
I
take
didn't see
themselves.
that one. Send it to me. I saw a bunch of CS.
Well, Nir, thank you so much. I appreciate it. I wish we had more time. And in fact, if you've got a video of this or something, I think some of us would like to see the balance of the presentation. But it's called a day for the formal part of the meeting. Let's move on to the golf meeting. And